of, I think somebody mentioned it, the treatment plant and collection system is complicated. It's very complicated. And there's a lot of components that go into a design. We are only one piece of the design, so there are a lot of elements that are not necessarily under my design or scope. So tonight, what we are designing is the collection system. So that's the sewer pipes that are technically owned by the district, and they would be mostly in the public right of way. There are times that they end up with easements through private properties, but that is the publicly owned infrastructure. And then also the treatment plant itself. And from the treatment plant, we were not designing the components within the treatment plant, but more or less laying out the components of the treatment plant. In collaboration, I guess I should add, in collaboration with a packaged treatment plant manufacturer. Next slide. So the district was broken into 3 zones. At one point, they might have been called phases. There's a number of documents going back 10 plus years in how it was broken down. And zone 1 is the downtown lots, which is a mixture of commercial and there's some residential. And that's important from a design standpoint because what the waste comes from commercial is different than the waste strength per se that comes from residential. So it's important when designing a treatment plant that you know what the makeup is. Zone 2 is the small residential lots that surround that area, and there's a map on the next page. And zone 3 is the remaining lots. Obviously, that's a much bigger portion to the first 120, the 264, the remaining lots within the district boundaries. Next slide. I know it's small, but this is how the zones are broken out. So green is all the infrastructure associated to collect the wastewater within the commercial zone. The fuchsia is the remaining lots outside of that. And then the bulk of the area is the remaining residential throughout the rest of the district zones. So that's zone 3. So in designing, as I told you, in designing the treatment plants, it's important to understand what needs to be treated, what has to come out, has to be separated into the various streams. And so what we did is we took all of the zones and we broke it down. We went lot by lot. What is the use and what are typical flows or typical, so flows and strength of wastewater. You're on septic. Best information you can get is when you test it. We don't have that ability when you're on septic. There isn't a waste that we can test as we're going along. So we're using, other known areas. The treatment plant manufacturers work with this regularly. So there's some typical strength and flows that we're working with. And then those get applied to the number of lots within each of those zones. And then we break that down into what's your average daily flow, what's your max flow. And then as you go out, what we were tasked with was what happens at 20 years. And I know there's, you can't do much. There's porta potties for the public, there's other things. So what does that look like? Obviously, none of us have a crystal ball, so we use typical information to try and get there. So the projected flows at that 20-year build out for each of the zones is here. And the important information is what we use are the maximum daily flows. And what's important there is that you can contain it. So when you've got max daily flow coming in, it's going to happen in a diurnal curve. So you've got when everybody's using it, it's a peak, and then when everyone falls off for the night, you end up with low flows. So your treatment system has to handle both ends of that. And then also the strength. So if you bring on zone 1, it's going to have a higher strength, is what we refer to it in wastewater design. So it's a higher concentration. And when you bring on your residential, you tend to get more water, less concentrated, more diluted, and that helps you in a treatment process but obviously there's still more flow to take care of. Next slide. So this one, I just want to get a kink in my neck. This is the process, and there's a bunch of components that go into the treatment plant. The first piece of it is collection, and it's the raw sewage. It's what gets flushed down the toilet. It's what gets through your laundry. That's what is flushed through the collection system and collected. But when you're working with pumps, you're not gonna pump at those diurnal probes. So you're gonna collect it in what we call a wet well. It's gonna hold your raw sewage, and it's gonna be pumped into the treatment plant so that you have a steady flow, or a relatively steady flow. You're able to control your flow, and you're able to understand what your tolerances are. With wastewater, you can't shut it off. There is no way to shut it off. Right? You're going to continue flushing. You're going to continue. So you have to have a size that can capture those max flows. So that's one component. And then that goes into an equalization tank, and that's where it starts mellowing out those diurnals, and you're getting more of a constant flow that you can pump into your system or flow through your treatment plant. The other part here is odor control. And I know that smell, the odor of wastewater, it's poop. My family, we talk about poop a lot. This is what I do. It smells. It does. It has an odor to it. And so that is a piece. Every component has an odor control associated with it. This gray box represents the package manufacturer plant. So I know that there's been talk about a size and these package plants. The components that are taken care of within that are just one piece of the puzzle, and that is what plays into a size. And it really varies depending on what you end up doing with the waste stream at the end. So how far do you take your treatment level? So there's obviously options that have been discussed, I know, a number of times that I've been involved in. But if you were going to inject it with a well at your highest treatment, that's almost drinking water standards. You're cleaning that water up to the max. If you're talking, and this is just for example, but solving, their wastewater treatment plant doesn't go to that level. There's secondary standards, or there's tertiary. So there's different levels of treatment, which would determine how big that package component is and how many parts that you need. Another thing to consider is once you start bringing waste in, you do have to take out your inorganics. So you'd be surprised to find that at what they call the headworks, is right at the entry of wastewater treatment plants, what gets flushed down a toilet or what gets sent down a drain. You find bed sheets, you'll find towels, you'll find money, you'll find just, honestly, you name it, there is a wastewater treatment plant operator in the state that has found it. So that's got to come out, and that is a piece. That smells bad. It does. That's the worst of it. Pulling out those inorganics, and then that has to be hauled out. So that's another component before you can even treat your water. Because what your wastewater does, your wastewater treatment plant, is it treats the organics in the water, not the inorganics. Those have to come out. And so that leads to two trains. So once you've got your inorganics out, now you treat it, and you have a liquid stream and you have a solid waste stream. You can imagine what's in both of them, but your liquid stream is the one that's going to be the cleaned up water, and your solid stream is think of it as fertilizer, is what you end up with. And sometimes it goes into fertilizer. Well, if you've got wet fertilizer, is what comes out of it, there are options that have to be decided upon. Do you try and dispose of wet fertilizer? It's technically a hazardous material, and it's tough to transport. You're also pumping, it's heavy because it's got the liquid in it still. And so there's considerations I know I put some fun little trucks, but there's considerations that go into each of these steps. Treatment plants will use belt presses and squeeze the liquid out so that the liquid stays and gets returned back into the treatment process. And then they take the fertilizer and haul that. It's cheaper because you're not hauling the extra weight. Those details are details. Those are final design details. So what we've got here are all the components that you need and the space requirements. There's some assumptions in there, which is how we got to a 1.6 acre treatment plant, was so that we had space for each of these components. So that's your solid piece. And then your liquid piece depends on your treatment level. If it needs to go through UV for disinfection, that's another component. So that's outside of the package manufacturer plant. And then when you discharge it, it's the same as when you're receiving it. You don't want to discharge in these constant ebbs and flows and big peaks and lows. And so what we've accounted for is storage to allow for a continuous disposal. And that's typical in, let's say you're disposing to a creek. That's beneficial water and gets used. And it's good to be a little bit more consistent on your disposal. I did want to add, so if you do use UV for RO, I don't know if anyone has, some people have RO at their house, there's a waste stream because you're pulling more out of that. And that would also have to be disposed of and hauled out. And there are places that you can take it, but it wouldn't be handled here. So you end up with at least 3 to 4 places where you're hauling something out. It's amazing what we can get in wastewater and how you got to separate it out and take it out. So all of those pieces require a truck or some sort of transport to come in. So part of the layout includes access, turnaround, space for these large trucks to enter. And I think that walks through the basic process. What's not shown on here is the ancillary power. All of the chemicals, because all of these processes do require chemicals. So there's chemical storage, there's chemical pumps, and then there's the management of it, the computer programming, if you will. Some do it, some plants are by hand, and some are by computer, and some are broad range in between. So you've got, operator access and those types of things. So we'll go to the next slide, because the next slide is our layout. And we took all of those items and we laid them out. We laid them out at a preliminary level that said, okay, if you're going to equalize your wastewater coming in, which we would recommend, you're going to need a tank for it. And if you're going to equalize your disposal, you're going to need a tank for it. What you'll see here in the blue is intended to be inside a building. And I know we had talked about a building, and nobody wants to see it. Nobody wants the poop. They want it to go away and be hidden. And what comes with that is you gotta make sure that it's safe for people to enter. And so when you do enclose it, you add equipment, because you add air scrubbers, and you add basically air scrubbers that keep it safe for someone to enter. So it's very hazardous substance, and the gases that get created with wastewater. And so safety is an important factor in the layout, access, and how you'd maintain it. On this site plan, we are showing space for injection wells. That was just for space consideration. I'm not the hydrogeologist, that's not my background, but there are limitations as far as spacing and all of that. So they're really shown more just schematic to say, hey, you could look at this area. The layout here does show 2 access points. There isn't a site that we're designing to. We do not have a final site. So our site was, if we were the operators in ideal, we would want a way to get trucks in and a way to get trucks out versus having to have a turnaround spot for a vehicle. So what we do is we lay out a vehicle and we lay them on to make sure they can make the turning radiuses. The other aspect to this is there is a buffer of landscaping and fencing around the outside. The key piece is security. You definitely don't want anyone accessing your treatment plant. With that, we can go to the next. So these are just some examples that some treatment plant manufacturers had provided. Now, I get it, it's in the snow, so that's not the same landscaping we get here. Understand. It's not often that they put it in a building. So there's not a lot of buildings. So these were some examples I had. And the other piece I will say is I don't know the design or the amount of flow that goes through these. So I'm not saying that this is exactly what is here. It's just a visual. Next slide. So the gravity sewer collection system. When you lay out a system, there's some design criteria that you've got to lay out and set forth. And the district eventually will adopt standards, whether that's similar agencies that are around that develop their own. For now, we gave some recommendations based on pretty common. Honestly, sewers have been designed way before I ever started designing them, so it flows downhill, gravity. So the understanding was preference for gravity sewer. The minute you introduce pumps, there's more things to go wrong, there's more things to maintain. If you can gravity flow, it is ideal. It doesn't mean that you can't add a lift station or a pump station somewhere if you need to. So the very first round we did was, can we do this whole thing by gravity? Minimum of 6-inch diameter sewer mains. That's for being able to clean them out. You will want to inspect, clean them regularly. That's what comes with owning a sewer system. Minimum of 0.5% slope, and that comes down to how much solids collect on the bottom. Again, that's maintaining. So if it's designed properly and constructed properly, I will warn those are 2 different things. You would want the solids to go also with the liquids. If you have not enough slope and it settles out, you'll have buildup. And then a maximum slope, 10%. You have the opposite problem, and high velocities can cause other issues. It can cause odor issues and other problems scouring inside your manholes and additional maintenance issues. Limited pump station is similar to the gravity sewer. Minimum 6 feet cover over sewer mains. Minimum 4 feet cover over sewer laterals. And the sewer lateral is the privately owned portion of the pipe, which would connect to a sewer main, which is the publicly owned portion. And then a maximum of 500 feet between manholes, and you would put a manhole at any junction, any pipes coming in together. And the spacing requirements is really cleaning also, access, and what's a typical jetting or camera length. Next slide. So we broke the zones up. Right now, what we were asked to do was to design the entire system and what that would look like if you then broke it down by zones. And so what's shown here is the infrastructure and the backbone that you would need to serve the zone 1 if you were going to go forward with all 3 zones, and that was your future plan. And so it goes to the bottom, and it's all gravity. And there would be a pump at the end, and it would either pump to a close by site plant or a treatment plant, or it would pump. You could pump anywhere at that point. And the construction costs right now are $30 million for that. And that would be the treatment plant and the collection system. And it's not cheap. And if you got that price a few years ago, it would be less. Prices have soared, and that's unfortunate where we are right now in pricing. Next slide. So zone 1 and 2, if you were to construct 1 and 2, that's the added infrastructure. It's 32 million, so it bumps it by a little. You basically need everything in zone 1 and then a little extra pipe. Your treatment plant would be similar, would be the same. And then if you go to the next one, it would be the whole system. And the entire system would be 47.8 million. Next slide. As I mentioned in the beginning, the sewer mains are the publicly owned sewer, and then within the right-of-way or potentially in easements. In order for this current plan, it's the first, it's probably not the first, I know there's been studies, but it's our first stab at it. There's some other utility corridors we tried to stay along. There's separation requirements from water. So all of that played into some proposed private easements. That's obviously further down the road in discussions, but the way that the streets are laid out, if you're gravity down, and that's the end of the street, it's really hard to gravity up the street and then back down. So there are some proposed private easements. And then the laterals, the same thing. There are flag lots. There are lots that are behind others. There are lots that are on private, shared driveways. And so there would be a need for private easements and private negotiations between property owners in those scenarios. In those cases, there wouldn't be a public main that fronts one of the private properties. Next slide. And then the laterals. So the laterals are private. That connects to your house plumbing or business plumbing, and then would be a new pipe that goes from that plumbing connection to the street. As you can imagine, we don't know your depth of plumbing. There's some building codes. There's some minimums that they have to be, depending on when you were constructed. Also, building codes do change over time. So, to our best ability in a preliminary setting, we've estimated those. What we did do, though, is highlight properties that to us stood out that may need additional information or further research. They will all need to be evaluated on an individual basis, but for these, there may be a balance between lowering a sewer or a private pump. And those are decisions that we're going to be each individual case-by-case basis. But what we wanted to make clear was that it's not straightforward for every single property when you start with a public main in the street. Okay, so the proposed costs are preliminary proposed costs, and they are based on looking at the collection system as a whole and breaking them down into zones constructed. And then also the reason the north option is higher is that you have a force main that we had to make an assumption that it goes somewhere to the north. So there's an assumption that there's an added force main pipe. Next slide. That's the end of my presentation. I am happy to take more questions or whatever's next.
So, in my hurry to get the presentation, my concern about this is I forgot to mention my comments about grants, and we neglected to let the engineer type make this opening comment. So, if I could real quick right now.
Let's go back and have you, and then have Mr. Pike come back.
Yeah. So I was just going to introduce this.